Hi all, I am Dr. Raghuram Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process, and today's topic is Basic Working Principles of Electrochemical Machining. Okay, right. Now let us discuss the course learning outcome of the topic. At the end of this session, student will be able to understand the electrochemical machining. Okay, right. Basic working principles. So before we discuss all these at a glance, let us see the sequence of this topic. Okay, so that we'll have idea. Okay, where we have to emphasize the things. Okay, right. So here we have to focus on the certain areas to understand better. Okay, basic working principles. The simplest case to consider is that of plain parallel electrode normal to the feed direction as described by Tipton during 1971 as shown in the figure 1. Okay, so working gap with plain parallel electrodes at a constant gap voltage. So here workpiece and tool, these two have connected. Okay, so here U in, and this is the potential difference, that is voltage. Okay, so here this will be X, Y, Z coordinate system, constant feed on workpiece. Okay, right. Consider an electrolyte of conductivity K and density rho E, that means electrolyte density, that flows at a mean velocity U in the direction of increasing X in a channel. The channel is assumed to extend to the left of the origin X equal to 0, where the tool and the workpiece starts, so that the flow has reached a steady state and the inlet conditions can be neglected. See, look at this. It has started at the X equal to 0. Okay, so that's what we have discussed. So here electrolyte conductivity K and the electrolyte density rho E. Okay, and its mean velocity U. Okay, and in the direction of increasing X in a channel. Right. All properties of the system are assumed to be independent of the Z direction. Okay, all properties of the system are assumed to be independent of the Z direction. The position of the workpiece surface relative to the tool, and hence the gap thickness is represented by the coordinate Y. Okay, see here this is Z, this is Y. Okay, right. The workpiece surface moves away from the tool surface in the direction of increasing Y at a rate proportional to the current density J and equal to, okay, see, this is the governing equation. Okay, now let us discuss what is all these things. Okay, just look at this and you understand. Okay, this is the governing equation that we have taken directly from the experimentations. Okay, so later we have discussed all these things. Okay, so at the feed rate A in the direction of decreasing Y, the workpiece rate of change of position dy by dt can be written as this one. Okay, so directly we have differentiating with respect to time, so that we got this governing equation. Okay, so where is gamma equal to current efficiency of the dissolution process in percentage. Okay, this one. F, Faraday's constant. So that is 96,500. Okay, C by G per ion. K, electrolyte conductivity. Okay, so ohm inverse, mm inverse. Rho, density of the anode material. Okay, gram per cubic millimeters. And zeta, chemical equivalent weight. Okay, and V equal to applied voltage in volts, and delta V equal to over voltage V. So these are the various parameters associated to this governing equation. Right. The current efficiency, this is, let us say, not gamma, this is K. Let us say the symbol is some other zeta. Okay, is defined as the ratio of the observed amount of metal dissolved to the theoretical amount predicted from Faraday's laws for the same specified conditions of electrochemical equivalence, current, etc. Okay, apparent current efficiency values may be due to the choice of wrong valence, passivation of the anodic surface, grain boundary attack, which causes the removal of metal grains by electrolyte forces, gas evolution at the anode surface. Okay, right. It is convenient to write the machining constant C for the particular workpiece electrolyte combination. Okay, that it has been written like this. Okay, look at this C and differentiate that y with respect to t. Okay, so that we get like this. So upon integrating with time limits 0 to t, then we get the equation like this. Excuse me. Excuse me. Right. So all these are the equations through deriving from the different equations and experimentation based on these constants, it has been formulated. Okay, right. So finally we kept the final equations. Students should be able to understand, and you can derive from the beginning of the equations, right? And t here y0 to y limits. Okay, so this will be like this. So this will be the final equation of that t, right? Now attainment of equilibrium gap at a constant feed rate and various initial gaps. Okay, attainment of equilibrium gap at a constant feed rate and various initial gaps. Okay, so in x-axis machining time and in y-axis equilibrium gap y. Okay, so here gap width. Okay, gap width y and machining time t. Okay, right. Figure 2, that means this one only. Figure 2 shows how y varies with time approaching equilibrium value ye asymptotically. Okay, asymptotically the y is varying. Okay, for the case of 0 feed, that is a equal to 0, dy by dt equal to c by y. If the initial position of the workpiece surface at t equal to 0 is y0, then y equal to square root of y0 square plus 2ct. Okay, so all these equations have been derived from the different equations. Variation of initial gap with machining time at 0 feed. Therefore, the gap increases in proportion to the square root of the time as shown in figure 3. The gap increases in proportion to the square root of the time as shown in figure 3. Okay, at a constant feed rate A, the workpiece surface will be stationary and hence the gap thickness becomes constant when dy by dt equal to 0 or y equal to c by a. Okay, see here machining time in x-axis and gap width in y. Okay, so this is the initial gap y naught. Okay, so this will be representing variation of initial gap with machining time at 0 feed. Right, so this is the equation at the end, y equal to c by a after differentiating with respect to t and equating to 0. Okay, right, under such conditions the metal removal rate per unit area is equal to the feed rate and the corresponding gap thickness is called the equilibrium gap y. Okay, as shown in figure 2, if the gap thickness is greater than ye, the metal removal rate is less than the feed rate. So the gap closes upward ye. If the initial gap is less than the removal rate is greater than the feed rate, so the gap always tends towards the equilibrium value ye. Okay, as the process proceeds. Okay, so here ye is the important parameter. During ECM drilling, decreasing the feed rate leads to wider machining gaps and hence a lack of dimensional accuracy. Okay, on the other hand, too small of a gap causes sparking or a gap short circuit that could damage the tool and workpiece. Okay, so here too small of a gap is also danger. Okay, which causes sparking or a gap short circuit. Okay, that could damage the tool and workpiece. These are the process characteristics schematic. Okay, ECM process components. Okay, so this figure depicts figure 4. ECM relies mainly on the ECD phase that occurs by the movement of ions between the cathodic tool and the anodic workpiece. Okay, so here the cathodic tool and anodic workpiece and electrolyte is passing between the gap of tool and the workpiece. So here ECD phase. Okay, so this causes making ions and those will impact on the tool. Okay, right, material removal rate. Faraday's laws describe the rate of material removal for pure metals. The specific removal rate QC is given by the scientist Kaczmarek. Okay, so that is 60 zeta by 96,500 rho. Okay, for a machining current I, the volumetric removal rate QV is given by this equation. Okay, right, just this one is over. Okay, for a machining rate I, the volumetric rate QV, that is in mmq per minute, is given by QCI. Okay, right, the linear removal Q1 is a function of current density J. Q1 equal to QCJ. Okay, where J equal to this one. Okay, V minus dV into K by Y. Okay, so this text inform that the specific removal QC describes how effectively the machining current is utilized for the material removal from the workpiece. The higher the value, the better is the removal rate per ampere. Okay, since most metals dissolve at different valences, the exact determination of the theoretical removal rate becomes difficult due to the random phenomena occurring in the inter-electrode gap. Okay. Next, confusion may arise when the incorrect valence state is attributed to the dissolution process. In this regard, at a low potential difference, nickel usually dissolves in a divalent state in nitrate and chloride solutions. This mode of dissolution switches to the trivalent state at higher potential differences. Similarly, copper has been observed to dissolve in a single valence in chloride solutions and in a solution divalent state in nitrate solutions. The apparent valence of copper dissolution changes also with the mode of dissolution. In nitrate and sulfate solutions, copper dissolves with a valence of 2. For conditions of transpassive dissolution, this valence has been found to be between 1 and 2. Okay, and approximately 1.6 at 60 amperes per square centimeters. So this information is completely based on the research outcome of the researchers. Okay. So at the end, ECM is mostly carried out on hard materials and alloys. For an alloy containing n components of varying percentages, the prediction of the removal rate becomes more difficult. The volumetric removal rate, which is very important, QV, that's what we are discussing so far.
Like, share and subscribe. Hit the bell icon for more updates.